Morning.
Morning. How's everybody doing today?
Good.
Good. Anybody get to do anything fun or interesting over the weekend? The long Labor Day weekend? I know it's so different right now.
You heard of the new fire, right?
Which one?
The one that started because of a gender reveal?
Oh,
Yeah.
Oh, that's actually like 10 minutes away where I'm from. The fire, like the whole sky is like gray
oh
right
my
now.
God. I'm really sorry to hear that. Are you safe though?
Yeah.
Okay. Yikes. I have opinions on stuff like that, but I'll save those for another time. All right. So let's jump in and get started. So first off, good morning, everybody. Really glad to have you all here on this beautiful Tuesday morning after a long weekend. Hopefully you didn't melt over the weekend with how bad it was outside heat-wise. Interestingly enough, our friends over in Denver went from 90 degrees yesterday to snow today. So weather can be very extreme. So let's jump in. So what I thought I would actually do today for the participation question and for also helping out with homework is I thought I would give a question similar to one of the homework questions. We can go over it. And my goal is to do everything I can before the end of class today to help you feel 100% prepared for this homework assignment. Okay. So let me plop this into chat. I also did put it up on Canvas. Whoops. Sorry, my mouse is very sensitive. Okay, so here's the question. In January of 2000, so at the beginning of this millennium, carbon dioxide concentrations were at 369.14 parts per million. In January 2020, they were at 413.37 parts per million. So the two questions I want to ask are first, how much has carbon dioxide concentrations increased since January of 2000? I should have put January in there, but so how much have they risen since January of 2000? And then the second question is, how much have they risen per year? And a hint that I'll give you is whatever number you come up with here, divided by 20 down here, because it's been 20 years. So whatever the total change is, divided by 20 years, and that splits it up into individual years. So take a moment, noodle this. And then what I will do is I will go over how to do it. Once again, because this is a warm-up question, there's no penalty, there's no right, wrong, anything like that. I just want to see how you're doing with this, and then we'll go over it. And I will once again plop this in chat. Oh, oops. Sorry. All right, take another minute. For those who've just trickled in, I can post the link one more time. And let's see here. Okay, so far 34 people have responded. Okay. Okay. Looks like another person or two still needs to wrap this up. Not a problem there. But it looks like I've gotten responses from just about everybody. And what I'm seeing in the responses, I'm dual screening it using my phone to look at the responses. They look pretty good. They look pretty good. All right, so let's actually talk about how we do this. Because I know for some people, this kind of is like a deer in the headlights sort of thing. And so definitely want to get this demystified. So the first question deals with how much carbon dioxide concentrations have risen since 2000. And the way to solve this is you take what the concentration was in January 2020. That was the 413.37 parts per million. And then you subtract what it was in January of 2000, which was 369.14 parts per million. And so whatever this difference is, that is the answer. And in this case, it was 44.23 parts per million. So that is how you solve that first question. And this is pretty much almost identical to what you see on the homework. The only difference is that in the homework, we're using a much bigger time period. So we're using 1958 to 2018. Okay, somebody else just asked for the link to the warm-up question. So that's the first thing. The second thing is Now you're looking for an average. So on average, how much have carbon dioxide concentrations risen per year? So the way to calculate this average is the same way that you would calculate a rate like you do in an algebra class. How many of you have ever heard of rise over run before? I see some hands. Well, you're literally doing the same thing here. You're calculating the rise, which is this right here. This is your rise, your change in carbon dioxide concentrations, and you're dividing it by your run. That's how many years have elapsed over this time period. So basically it's total change divided by number of years. And in this case, it's 44.23 parts per million divided by 20 years. And that gives us an average of 2.21, and then some other stuff, parts per million per year. And one of the things I'll say, like whenever you do a math problem in this class, I know scientists talk about significant figures and how many digits. I always tell people, if I see those first two digits, I'm happy. So if I see those first two digits, I'm happy. So 2 decimal places, anything after that, you can just round and my feelings won't be hurt. I think it was actually 22.115. Or 2.2115 parts per million per year. Now, actually, something I'm interested in seeing now that we've done this is how does this rate of change compare to the rate of change over the entire period? Because if this rate happens to be higher than it is over the entire period, that would indicate that carbon dioxide concentrations are not only increasing, but the rate at which they're increasing is becoming faster. That's a bad sign. We wouldn't want to see that. Okay, so that was for question number 1 for the homework. But I also wanted to talk about question number 2, and then maybe kind of go over the other questions real quick, just to at least kind of help give you a springboard into the assignment. Okay, so question number 2. So for question number 2, I provide you with that graph that shows global average temperature anomalies. It doesn't actually show you the actual temperatures. Instead, it shows you the anomalies, basically the difference from the late 20th century average. And so wherever you see a positive anomaly, a plus number, that represents a time where temperatures were above average. And then wherever you see a negative number, that means a time where temperatures were below average. If you'll actually look, pretty much the past 30 years have all been above average. In fact, like way above average. And so one of the things I'll recommend is that in addition to that graph, there's a link that you can click on. And that link should really quickly, let me actually go to the site. That link should actually take you to something like this. And this is basically just a super primitive text table showing you each of the years, the temperature anomaly for that year, And then over here, this is what's called the 5-year average. We're not going to worry about that for this question. We're just going to focus on the year and its temperature anomaly. So for the year and its temperature anomaly. So that's the first thing. And what you are instructed to do, what we're looking for in this assignment, is first off to identify where the highest anomalies are, and then the second, third, and fourth highest anomalies. I'll give you a hint. They've all been in the last 5 years. So that's the first thing. The second thing is identifying where was the last time we saw a negative anomaly, a temperature below average. I'm not going to give away the answer, but basically start at the bottom of this table, work your way up until you see that first negative number. So the other thing for this question on the homework, whoops, let me go back to the PowerPoint screen. Is, whoops, I'm so sorry, my mouse is so sensitive. Okay, here we go. So the last thing is that you'll be asked to calculate a temperature trend for the past 40-ish years. And basically, how much have temperatures risen in the past 40 years? And you'll be given, just like with the last case, you'll be given a current anomaly. So let's say the current anomaly is 0.85. And then the anomaly from, oh, actually, let me, always got to put your unit down. Okay. And then you'll be given an anomaly from like 40 years ago. And let's say that anomaly was 0.15. Well, total change would equal, whoops, oh, sorry about that. I blundered there real quick. I put the equal sign in two places where it wasn't supposed to be. Here we go. Let's get rid of that one. There we go. And so this would give us a value of 0.7 degrees Celsius. So that's how much the temperature anomaly has gone up over this period of time. The second question is to then convert this to Fahrenheit. A very common mistake that people do here is when they convert it to Fahrenheit, they accidentally shift it like you would if you were to convert any like actual temperature. Here's what I mean. Like normally when you convert Celsius to Fahrenheit, you take your Celsius temperature, you multiply it by 1.8, and then you add 32 to it. The purpose of adding the 32 is that 0 degrees Celsius is 32 degrees Fahrenheit. It's the freezing point of water. But here we're not looking for an actual temperature. Instead, we're looking for a change in temperature. We're just looking for an increment in temperature. When you do that, you don't add the 32. So for example, if I'm going to convert this to Fahrenheit, I would take the 0.7 and multiply it by 1.8, which would then give me a value of, calculators are totally fine to use, 0.7 times 1.8, 1.26 degrees Fahrenheit. (1.26 degrees Fahrenheit). Now these are numbers I just pulled out of my head. These aren't the actual numbers from the homework assignment because I don't want to give away the answer. But this just gives you that idea of how to do that conversion, how to look at that whole thing. The last part of this question, question number 2, is you're asked to comment on the significance of your finding. Well, here's what I'm looking for there. What I'm looking for there is you'll actually get a total increase in temperature from 1880 to 2018. I'm going to give that to you. It's some number. What you're going to be doing is you're going to be looking for a temperature increase just since 1978. Or, let me see here, actually 62 years. Yeah, it's going to be, I'm trying to remember the exact year I assigned. I always switch it up slightly from semester to semester. Let me actually go to that real quick. Here we go. (1977), not 1978. So 1977 to 2018. And that's going to give you some other number. Well, the idea that I'm trying to get you to see here, and the significance I want you to look for, is has most of the warming that we've seen over the past century and a half occurred during this more recent time? So has most of the warming been recent? So has most of the warming been recent? That's what I'm looking for there. So if you come up with a number for 1977 to 2018, and it's almost as big as the number from 1880 to 2018, what you can say is, okay, well, most of our warming has happened in roughly the last 40 years. As a result, warming is accelerating as well. Warming is actually getting faster. We're getting warmer quicker. So that's what I'm trying to get you to look at there. Just that concept of, hey, has most of the warming that we've seen over the past roughly 140 years, has it been recent, or has it been much more gradual over the entire time? So that's what I'm looking for there. As far as question number 3 was concerned, question number 3 was, we had a sudden cooling period in the early 1990s. What do you think caused that? I actually did mention that in class a couple of weeks ago when talking about recent climate change, like what's actually happened recently. I'll give you a hint, it has to do with a volcanic eruption. That's about all I can say about that. For question number 4, I give you a graph of ice coverage area, and you're basically going to identify where the two highest peaks were, where the two lowest points are on the graph, and then make a prediction as to if this trend continues, if ice coverage continues to decrease, when would we get to a point where it is below 1 million cubic kilometers, or sorry, 1 million square kilometers? And then finally, for question number 5, that one is a little bit more open-ended. There's no right or wrong answer. Like, I just want to see what your thoughts are on that. So basically, 3 of the 5 biggest snowstorms in New York history have happened recently, over the past 10 years or so. Does that disprove global warming? And there, I just want to see your understanding of like what the difference between weather and climate is, and what the difference is between global warming and climate change. So with that said, I'd like to open it up now. Does anybody have any other homework related questions that I could help out with right now?
I think that was good. That was really helpful. It went over everything and cleared a lot of things up.
Great. Thank you so much. And I really appreciate people speaking up as well, saying, hey, I don't understand this. I'm always happy to demystify something. And I'll actually make sure in the future to do some more intentional time during class to do that. Thank you so much.
Yeah, thank you. Yeah, because I felt like other people were also confused as well, but like being with this like Zoom thing, people are kind of scared to speak up about the homework, so that's why I felt like it was a reasonable thing to ask. But that was really helpful. Thank you.
Absolutely, yes. And one thing I'll really stress is never hesitate to ask any questions in this class. There's no dumb question. There's no question that you shouldn't ask. I'm always happy to help, and I hope that really does show. Okay. Ooh, I got a good question that somebody privately sent me. How do we predict September Arctic sea ice to be below 1 million square kilometers? So on that graph that I showed, let me actually switch over to it. On that graph, on the homework assignment, there's actually a trend, or sorry, there's actually a trend line that is included on here. And basically what I'm going to try to get you to do is just take a guess, more than anything, as to when that trend line would dip below 1 million cubic kilometers, or sorry, I keep on saying cubic, 1 million square kilometers. So if we continue following that trend, when would we reach 1 million? I know it's off the chart. I know it definitely is a little bit more of a stretch. But I'm just looking for a prediction here. I'm just looking for a guess here. As long as you can justify your guess, I'm happy with that. One of the things that I've done in the past is I will actually stretch the image like so. So 2.5. I don't know why it keeps getting rid of that. I don't know why it keeps getting rid of my period, my decimal. 1.5 and 1, and then just taking a guess as to when sea ice extent will drop down to that. Another thing that you can also do is research it. Look up what are the predictions that are actually out there. As long as you cite your source, I'm happy with that as well. So there's a couple of different ways to go about that. Does that kind of help? Okay. Please don't hesitate to ask follow-up questions, though. Whether in the chat or whether unmuting yourself or speaking up, like, my number one thing, I don't ever want a student to suffer in silence. That is like my anti-catchphrase. I never want you to suffer in silence. I believe every one of you, the 45 people in this room, plus the other 5 that aren't here right now, I believe every one of you can do this stuff. I know that you can. And if there's something you're stuck on, or if you need a leg up or anything like that, I'm happy to do that. That's my goal as your teacher, is to just get you across that finish line. All right. So that being said, thank you so much for asking questions. Thank you so much for bringing to light any issues that you may have had with the homework. I really appreciate that, because that helps me get a gauge of how people are doing. And the last thing I want to do is have anybody end up be a deer in the headlights. I want to make sure that I get you away from those headlights. All right. So that being said, let's jump into today's lesson. So a very key element of climate change really hinges on the idea that what has been happening recently, and when I say recently, I mean pretty much the whole 20th century and then now to the 21st century, that what is happening recently is not business as usual. But how do we figure out what business as usual actually is? Well, the bad news is accurate temperature records only go back to 1880. Accurate temperature records only go back to 1880. They don't go back further than that. So we have pretty good data that gives us a really good idea of how things have been going on since 1880. But to be honest with you, before 1880, we really don't. We really don't have an idea, or at least we really don't have direct measurements from before from before 1880. So how do we actually figure out how temperatures were like before 1880? Well, that's what we're going to be talking about today. So some of the goals for today. First, we're going to talk about this concept called paleoclimatology. Basically, it's just a fancy word for looking into past climates. And we're going to explore some of the ways that paleoclimatologists do this. How do we look into the past? And then we're going to look at these things called proxies. And I'll tell you a little bit more what a proxy is in a few minutes. But how these are used to represent past climate shifts. So first I'm going to talk about how do we collect this information, and then how do we use this information? And it's all about looking into the past. Okay. So really quickly, last week when we were talking about the history of climate change, Guy Stewart Callender, David Keeling, climate modeling, and then the most recent IPCC report, the Intergovernmental Panel on Climate Change. One of the key findings of that report was that since 1880, global average temperatures have risen somewhere in this range right here, between 0.65 and 1.05 degrees Celsius. This is how much warming has occurred since 1880. Now, these results are based on data collected from many different sources, processed by many agencies using widely accepted methods, all coming out with very similar results. What I have right here are the 4 top meteorological agencies in the entire world. The NASA Goddard Center for Space Studies, the Hadley Center in the United Kingdom, the NOAA National Climatic Data Center. So NASA is sort of the space side of things. NOAA is sort of the atmosphere side of things. And then the Japanese Meteorological Agency. So these represent the top weather bureaus in the developed world. And these are the 4 calculations that they've made for how temperatures have changed. Now, if you take a look at these, now they all use slightly different data taken from slightly different sources, but they all pretty much paint the same picture. Earth has been warming, and it's been warming pretty drastically over the past 140 years. But how do we know that this warming over the past 140 years is something we should actually be concerned about? Well, to do that, we need to look at time before 1880 and see how temperatures were like then. Well, how do we do that? We can't go back in time. I'm not friends with Bill and Ted. I can't jump into a time machine and go back in time. But what can we do? What can our time machine be? Well, here's actually some of the results from this time machine. And then I'll tell you what this time machine is. What these actually represent, these blue lines, right here, this blue spiky wavy line and then the black smoothed out line, that's a 5-year average. What this actually represents is a reconstruction of past temperature values. So actually being able to go back in time and look at how temperature was like back in time. Now, how do we do that though? How are we able to actually identify that these were what past temperatures were and that temperature was relatively stable until roughly the mid-1800s? How can we do that? Well, the answer are what are called proxies. So how many of you have ever heard of the word proxy before? Has anybody here ever heard of the word proxy before? A few people. Okay. So, a proxy is like a representative for something. Basically, it's a substitute. So let's say I got sick and I couldn't teach class one day, and I had my friend Henry, a fellow Met 12 teacher, teach for me. For that class session, Henry would be my proxy. He would be representing me. Now he's going to teach it a slightly different way. He may emphasize things slightly differently than I do, but he's a representative of me. He's somebody who, hey, I'm sick, I need a substitute for this day. Henry's going to be my substitute. He's my proxy. Basically, a proxy is a way of getting something that we can't directly measure. And then what we do is we actually calibrate them using current observations. So this is how we know that they're actually accurate. We'll actually take a look at what these proxies say about today and compare them to what the current observation for today is. And the better we can do that, the more reliable these proxies become in looking into the past. Now, the good news is that proxies aren't the only thing we have. There's also written evidence and geological evidence. So different cultures have been writing for thousands of years. And so we actually do have documentation of major heat waves, of major weather disasters, of floods, of major cold years. Like, we actually have written documentation of those things as well as these physical scientific proxies. So that being said, what are these proxies? What are these substitutes? Well, there are three key ones. These aren't the only ones, but these are the main ones. And the three key ones are ice cores, tree rings, and sediment samples. Ice cores, tree rings, and sediment samples. So these are the three key proxies that we use to look at past climate. And each one of these things can tell us slightly different things. And then using these three things, we can then put together a pretty good reconstruction of what past climate was. Now here's the good news. Between these three things, we don't just get to look back 1,000 years or even 10,000 years. We can actually, using these proxies, actually reconstruct past climate for hundreds of thousands of years. Because there's some really cool features that actually get locked in time via these proxies. So let's talk about each one of these real quick. First, let's talk about ice cores. So most ice cores are drilled from Antarctica. Why? Because Antarctica is the world's largest source of permanent ice. Here's how these work. So in much of Antarctica, the temperature doesn't really rise above freezing. So any snow that falls stays there. Well, embedded in every snowflake, embedded in every layer of snow, is actual atmospheric air from that time period. What this means is that every layer of snow on the ground actually has locked in it actual atmospheric air from that time period. And then because it never melts, that record never goes away. At least in terms of geological time, like millions of years. Eventually, continental drift may cause stuff to happen, but that's beyond what we're talking about today. So basically what happens is it snows. That snow doesn't melt. A year later, more snow. That snow doesn't melt. A year later, more snow. That snow doesn't melt. And so on and so forth. And so what you end up getting is you end up getting these long tubes of ice that have actually built up for thousands of years and embedded in different layers of those tubes are some actually like pretty cool atmospheric evidence for how the weather was like at that particular time. And this gives us a long-term climate record. So those are ice cores. Now there's actually another way, or there's actually another type of core that we can get. In addition to there being these permanent layers of ice, and I'll actually talk about how to read these things in a few minutes. In addition to these permanent layers of ice, the same is very true with seafloor sediment. Every single year, dust, debris, dead organisms, I know it's kind of sad to say that, but dead organisms end up sinking down from the surface of the ocean. They end up sinking all the way down to the bottom of the ocean. Near the bottom of the ocean, it's dead. There's just nothing down there. Well, there's some stuff down there. There is actually a whole ecosystem, but we're not going to talk about that. Pretty much anything that falls down there is stuck down there. Then, as time goes on, more stuff piles up on top of it, and on top of it, and on top of it. And so just like these ice cores, we can actually get a really good record of past ecosystems, past environments, and therefore past climates by taking a look at sediment cores as well. Now, the way that sediment cores work is very similar to the way that ice cores work. So this ice core right here was taken from a drilling station at Vostok, Antarctica, a former Soviet, now Russian ice drilling station. And you can actually see it's actually internationally run. There's a lot of different nations that contribute to the science going on there. Well, in order to get a sediment core, we can't just plop a station up in the middle of the ocean. Instead, what we do is we actually have different ships that are specifically designed to drill ocean cores, to drill sea sediment cores. One of the key ones is called the JOIDES Resolution, J-O-I-D-E-S. Whoops. D-E-S. Resolution. I'll clean that up in a moment. So the JOIDES Resolution. And this little corny video right here actually demonstrates how the JOIDES Resolution works. It's corny, but it gets the job done.
The main purpose of the JOIDES resolution is to drill into the ocean floor and bring up sediment cores for scientists to study. These sediment cores can give us a lot of information about the Earth. Many pieces of pipe are put together under the derrick on the rig floor into what is called a drill string. The crew attaches a drill bit to the end of the drill string and lowers the entire thing through an opening in the bottom of the ship called the moon pool. Once the drill string reaches the ocean floor, coring begins. A long cylinder of plastic called a core barrel is lowered through the drill string, and the sediment cores are collected inside it as the drill string rotates. The core barrel is then pulled up to the ship through the drill pipe and onto the rig floor, where the technicians and crew collect it and begin to prepare it to be examined by the scientists.
Obviously corny music, but let's see here. Obviously slightly corny music, but the main concept here is that these are ways that we can actually look at sediments from the past. And so what we do is we send out these large ships. The JOIDES Resolution is just one of these large ships. And what they do is they will then go out to a location out in the middle of the ocean. They will then send down that drill into the sediment, and then send up these cores, which can then be analyzed by scientists to sort of identify, okay, what was actually going on here. The JOIDES Resolution is actually active, meaning this ship is currently doing expeditions even right now as we speak. I actually went to the JOIDES Resolution website prior to class, and what I saw was that it was a little outdated, I assume due to the whole COVID thing. And they were supposed to start a new mission in April of 2020. And so basically what the ship does is it would go out to these different areas out in the middle of the ocean and collect sediment cores and then return them to then be looked at. Now, obviously, COVID has wreaked havoc on all of our lives, but the JOIDES Resolution is still at it. And they go to all kinds of places around the world, including West Antarctica, including places out in the middle of the Atlantic Ocean, different climates from warm equatorial climates to cold polar climates. All these different locations where we can gather up this sediment so then we can look at individual climate zones and identify, hey, what the hell happened here in the past? So these are sediment cores. And here's actually how a sediment core looks like. What you'll actually see is it almost looks like a long tube of mud. But embedded in that are different colors, which represent different compositions. So this can actually identify maybe a major volcanic eruption that then changed the color of the sediment for a few years, or a sudden mass extinction. And if you actually take a look, these colors are very banded. They're very layer-like. In a little bit, I'll actually tell you how we look at these and what are some things we actually look for in them. There are two key things we look at. First off, we look at the presence of fossils because of the organisms that were present during a certain time. That actually tells us how the environment was like and maybe how it changed over time. The other thing that we look at are these oxygen isotopes. I'll talk more about that in a few minutes though. The third one that we look at, and I'm actually going to show you it a little bit more in a few minutes, tree rings. So every single year, trees grow a layer on them. And we look at the size of that layer to indicate how that year was like. We'll talk about that in a few minutes though. So those are the three ways we look into the past: ice cores, sediment cores, and tree rings. Okay, so that's how we get them. That's how we get the ice cores, that's how we get the sediment cores. The tree ring, you just cut into the tree, unfortunately. But how do we actually know what these things are saying? Well, once you get a sample, once you get an ice core or a tree ring or a sediment core, you need to do a few things. The very first thing you need to do is you need to date it. That's the very first thing you need to do. You need to date it. The second thing you need to do is you then need to look at the composition of it at that particular time and see what it has to say. What was it made of? What weird isotopes are present? What weird chemicals were present? Was there ash present? That could indicate a volcanic eruption. Was there some kind of major oxidation event that happened? Usually in that case, you'll see what almost looks like a rust layer. And then you look at things such as the presence of fossils, because once again, those can indicate environmental change. And for trees in particular, you look at how wide the rings are. So let's talk about this. All right, so the first step is before you can do anything else, you need to date it. Now, when I say date it, no, I'm not talking about going out for a nice dinner and buying it a nice bottle of wine and having a nice romantic date. No, I'm talking about this kind of dating, obviously. We're trying to see when, what time does this particular layer of sediment or this particular layer of ice actually represent? Well, the good news is Mother Nature actually does a really good job of leaving timestamps. Just like when you submit an assignment to me, I get a timestamp. It says, okay, you submitted the assignment at this particular time. Well, Mother Nature does the same thing. It actually will date in a very real sense, not in like a literal sense, but in a very real sense. It will actually tell us when something occurred. How does it do that? Well, there's a few different ways. So the few different ways are these things here called the principle of superposition and then radiometric dating. And these things can help us unlock major cataclysmic events. When was the last time Yellowstone erupted? How do we know that a previous era has actually ended? How do we know when the dinosaurs died? Everybody says 65 million years due to some big explosion, but how do we know that? Well, being able to actually look at these sediment samples and actually identify when they represented, like what date they represented, can actually tell us all of that information. So the two ways that we can do this: superposition and radiometric dating. All right, so let's talk about superposition first. So the way superposition works is actually not that tough. So for ice cores, every single year, a new layer of snow, every single year, a new layer of snow falls. What does the top layer of snow represent? What time is represented by that top layer?
Current time?
Current time. Yeah, most recent. The most recent time. Yes. And then the layer below that, second most recent time. Third layer below that, third most recent time, and so on and so forth. Well, that's all that the principle of superposition basically says. The principle of superposition says the newest layer is on the top, the most recent one is on the top, and then each successive layer below being older and older and older. So newest layer on the top, each successive layer below older and older and older. So this is the first thing that we can use to date something. The new stuff is going to be right at the top, and then progressively older as you go down. What's actually really cool, in the case of ice cores, believe it or not, Mother Nature actually gives us an actual year for each layer of the ice core. Here's how. So tree rings work the same way, by the way. So every year represents a year of growth. The most recent one is on the exterior. Then the one below, or the one inside, the first one inside is the second most recent year, then the third most recent, and so on and so forth. But ice cores actually have a pretty interesting feature to them. The way that ice cores actually work is based on wet and dry seasons for that region. Ironically, near the poles, those locations get most of their snowfall in the summertime. They get most of their snowfall in the summertime. And the reason why is because a warmer atmosphere is a wetter atmosphere. I know us here in California, we don't think that way. We think, okay, summers are dry time. Well, that actually has to do with like large scale weather patterns that go beyond the scope of this course. But in most polar regions, they get the majority of their snowfall during the summertime. Meanwhile, during the wintertime, it's typically very dry. Well, this actually leads to a pretty cool feature in ice cores. If you actually look at the color of the ice core, what you'll notice is you'll notice these stripes. Light, dark, light, dark, light, dark. During the summertime, there's new snow falling. And that new snow usually stays nice and bright. Then we get into winter. During the winter time, no new snowfalls. But any kind of dust that's been kicked around, anything like that, falls onto that top little layer of snow and darkens it. And so that gives us slightly darker layers. So every bright layer represents a summer, every dark layer represents a winter, and then a pair, one summer, one winter, that's a year. So we can actually look at these and identify, okay, when were the summers? Those are the brighter. When were the winters? Okay, those are the darker. And then that couple, the light summer and the dark winter, that represents a year. And we can actually keep counting back and counting back and counting back in these ice cores to go back tens of thousands of years, hundreds of thousands of years even. So it's actually a pretty cool feature. Tree rings themselves are also very cool because they actually give you like a set layer. Now, unfortunately for sediment cores, it's not that simple. Sediment isn't lighter in the summer, darker in the winter. Instead, sediment cores might actually be very monochromatic, meaning very similar colored all the way down. Or you might see some layers maybe representing a volcanic eruption or a mass oxidation event or some kind of major cataclysmic event. But we need something else for sediment cores. Well, say hello to radiometric dating. How many of you have ever heard of carbon dating before? A few people. Okay, I see a hand or two up. Taking a look here, I see a hand or two up. Okay. Not everybody. Okay, somebody hasn't heard about it before. Well, we're going to talk about it today. So, here's how it works. Carbon is an atom, it's an element, and carbon is supposed to have a set number of protons and a set number of neutrons. Carbon is supposed to have a set number of protons and a set number of neutrons. Well, sometimes it doesn't actually work out that way. Sometimes you will actually have an atom with more neutrons than protons. So in a typical carbon atom, what you would have is you would have 6 protons. 1, 2, 3, 4, 5, and 6. And I'll actually write up here proton. Don't worry, we're not going to go super chemistry crazy right now. I promise. Okay, let me throw in some blue now. 6 protons, and then a typical carbon atom would also have 1, 2, 3, 4, 5, 6 neutrons. And then surrounding it would be these shells of electrons. Then surrounding it would be this shell of electrons. I'm not going to go so much into the electrons because for isotopes, they aren't as important. But a typical carbon atom has 6 protons and 6 neutrons. Well, sometimes when an atom is exposed to sunlight, sunlight can actually change the chemical composition, or not the chemical composition, but can actually change the particle composition of certain elements. And one of the things that can oftentimes happen is you can get carbon that'll actually have 2 additional neutrons. And so the total atomic mass of this, which is simply the number of protons plus the number of neutrons, ends up being 14 instead of 12. Because normally it's 6 protons, 6 neutrons. But in the case of carbon-14, you have 6 protons, 8 neutrons. So in the case of carbon-14, you have 14, a mass of 14. This is produced by sunlight. Well, once something dies, it usually either decomposes and gets buried very quickly, we bury it, or something happens to it. Once it dies, it doesn't really hang around the surface of the earth much longer. Even just a year or two, it will end up getting buried. Well, as soon as it gets buried, those neutrons, those extra neutrons, begin to go away. What actually happens is that those neutrons begin to go away, and carbon reverts to its original 6 protons, 6 neutrons. We actually know how long this takes to happen, and it's what's called a half-life. So basically, if I have a certain mass of carbon-14, so I have this big mass of carbon-14, in one half-life, half of that will actually convert back to normal carbon-12. The other half will remain carbon-14. Then, a second half-life later, I'll only have a quarter of that carbon-14 remaining. Then another half-life later, I only have an eighth, and then a 16th, and then a 32nd, and so on and so forth. Carbon-14 has a half-life of 5,730 years. That is carbon-14's life. What we can actually do is we can actually calculate how much carbon-14 is in something versus how much would be in it if it was currently alive, if it was currently at the surface of the earth, and that can actually tell us how old something is. Don't they use half-life for nuclear decomposition? Yes, they do. That's exactly what's going on. This is actually talking about like the breaking down of a certain isotope or a certain atom, a certain unstable atom. Great question. Thank you for asking that. Oops, there we go. And so the idea basically is that over time, the amount of carbon-14 present in something declines. And we actually know the rate at which it declines because we know that half-life. So using that, we can actually say, okay, well, this is how much carbon-14 is here. This is how much it would be here if it was still at the surface. We can now say that this was on the surface 10,000 years ago, or 12,000 years ago, or 15,000 years ago, using this rate of change. This gets a little bit into what are called differential equations. I'm not going to go that far into it. Like there's actually an equation we can plug and chug. It could actually give you like a set date almost. Like not like September 8th, 2020, but it can say, okay, this happened 15,532 years ago. We can actually get like a set year as to when this thing was buried. And that gives us a really good ballpark of its age. Now, carbon dating, because it has a relatively short half-life, really isn't good for looking anywhere back past about 30,000 years. The good news is there are other isotopes that are way better. Potassium-40, uranium-238, thorium-232, plutonium-241. These are all things that have a much, much longer half-life. A much longer half-life. And as a result, we can actually use these things, these different elements, to look back even further. So if carbon-14 is all gone and we can't use that anymore to accurately carbon date, we can actually use other things to look back even further. Now, what comes out of the other end of this? So we can date something, but what do we do next? Well, ice cores, tree rings, and sediment samples all do a really good job of locking in that current climate at the time that that sediment fell, or that snow fell, or that tree ring grew, that layer of tree growth occurred. And locked in each one of those things is a little bit of ancient atmosphere. So embedded in all that snowfall is a little bit, a bunch of bubbles of ancient atmosphere. And what we can actually do is we can extract those bubbles and look at their chemical composition. We could say, okay, well, in this case, there was much less carbon dioxide than there is now. And the composition of the atmosphere tells us that it was much cooler during that time. So this can actually tell us what was in the air and how hot or cold it was. It can actually give us a really good ballpark of that. That's pretty cool if you ask me. I mean, like that we can actually do that. That these things actually show us that. Another cool thing that can happen is when you get a major volcanic eruption, I'm talking about like Yellowstone style, all of that ash spreads around the world, and then it can then settle down onto a fresh layer of snow. And so sometimes even embedded in these ice cores, you'll see a ring of grayish ash that can tell you, okay, that was something, that was a major volcanic eruption. What about tree rings? So ice cores can tell us a lot about past atmosphere. Tree rings can tell us a lot about how good or how bad a growing season was. The study of this is what's called dendrochronology. Every growing season, so we're talking about spring and summer, trees grow, they gain a new layer. Well, the thickness of that layer depends on how healthy a growing season it was. For example, if it was a very dry year, that tree might not be able to grow as thick. It might not be able to get as thick a ring. Therefore, you'd see a very thin ring. Or let's say it was a very wet, but also very bright year. You might get a really thick ring in that case because a lot of growth was able to happen. So what we're going to talk about next time, we'll pick up on this next time, but what we're actually going to talk about is what is the ultimate result of all of this data collection, all of these different components? What do they actually tell us? So right now I'm basically telling you how we look back in time, but next time we're actually going to be able to look at an actual reconstructed climate. And there's some pretty interesting and some pretty scary results to it. All right, so this is a good stopping place for now. I will see you all next time on Thursday. If you have any questions, comments, concerns, I can hang out for a few minutes. Otherwise, have an awesome afternoon. Try to stay cool, try to stay healthy, try to stay safe. See you all on Thursday.
Thank you.
Bye.
Yes, sir.
Thank you.
Absolutely.
Professor, in case we would need help with the homework, the best way to reach you would be by email?
Yes.
Okay, perfect. Thank you.
All right. I just want to ask if the air quality right now, is it safe or is it not safe?
Ooh, well, there's a lot of factors that go into that. So where are you, first off, where are you located right now? Are you in San Jose?
Yeah, I'm around the Alum Rock area.
Okay, so you're in East San Jose.
Yeah.
Well, I'll definitely say today, I can just see from looking outside, today it looks not that good.
Yeah.
Let me actually take a look here at what the actual particulate matter is right now. Now, normally, you'll actually get what's called an air quality index value. You can actually look it up on your phone. And typically, anything below 100. So right now, my phone, in my location, it says it's 62. Which is weird because I think it's way smokier than that outside. And it says it's moderate. In that case, it's usually okay. You know, you're not going to get any big issues. What you might start to see are other values such as unhealthy for sensitive groups. That's for people who have asthma or have lung problems. That would be really bad for them. But for for people who don't have those problems, it might not be problematic.
All right.
Then you'll start to see unhealthy, very unhealthy, and hazardous. So the air quality index is the best thing to look at. And I'd say look up the AQI for your area right now.
Okay.
Great
All
question.
Thank you. I just needed to know. Thank you. Bye-bye.
Bye. Any other questions I could help with right now? I know a few people are still on. Totally fine if not. Okay, somebody is asking something. Number 4 from the quiz. Oh yeah. Okay. Give me 1 second. I'll just pull the quiz up and go over that question. Give me 1 second here. Okay. Number 4 from the quiz. Okay. So let's take a look at it. Oh my gosh. Let's see here. Oh, okay. Actually, thank you for letting me know this. So the key was mismarked. The correct answer is 0.85 plus or minus 0.2. And that was actually from, let me take a look here and see which lecture that came from. Okay. Let's see here. Was it lesson 2 or lesson 3? Okay, no, it wasn't lesson 2. Must have been lesson 3. Here we go. So this was in lesson number 3. Lesson number 3, slide number 23. And it was actually also covered in, let me pull it up real quick. Okay, lesson 23, slide number 23, and okay. And also lesson number 1, slide 20. So I could type those in here. Lesson 3, slide 23, and lesson 1, slide 20. Oh. Did she leave? Oh, okay. Absolutely. And if you have any other questions, please don't hesitate to reach out to me. All right. Bye. Have an awesome day.